All right, so I'm on start typing. All right, so I'm going to first look at GetPID. I know some people may have seen GetPID in chapter 2 or chapter 3, where it listed the main. Oh, this is still coloring some things. But what GetPID does, so this is, I'm going to remove a lot of the code from this, right? Just copy GetPID to GetPID 0.c. Right. I'm going to strip down this code just so that I just get the PID of the current process so we can see. So I'm going to remove a lot of this. Okay. Control. I'm deleting everything from the code file. Right. So the only thing that this code does is it makes a variable for the PID, which is called my PID, and then it calls getPID, and then I ask the user to enter something just so it will stop, right? And then I need to also print the PID, so print it. So my PID is right. So everyone is okay with this code. Gets PID into a variable and then prints the PID. Right. So I'm now going to compile this code. ECC get PID. And I'm going to output it to get PID 0. Right. And I'm going to run this. Right. So currently it says that my PID is 3667. Everyone can see what the PID is. Now this PID, people wonder where it comes from. If you do PS, this is a command in Linux, so it will list all the processes. And under some of the things you can do with PS, I just did man PS to get this. Right. There are options for man PS, there's PS-AUX, that means to list all of the processes that are on the machine, whether they belong to you or to someone else. Right. So if you're on a machine and you're wondering what's going on, PS will just give you your own things, but PS-AUX will give every single thing. So you can see there are many more things that are coming up. Right. This means everybody, you can see the PIDs, and one of them you can see is, need to. Right. One of them is this one, GetPID. And it's saying that GetPID, the PID is what? 3367. Sorry, 3667. Right. So everyone can see that that is actually the process ID of the thing that is running. It's not stopped yet. So when I say PS-AUX, it lists everything. And the last thing is, of course, GetPID. Now, if you're wondering how I'm switching from one terminal to the other, it's Alt. Alt F1 will give you the first terminal, F2 second, F3. In Linux, you can actually switch between multiple terminals. It's not like some operating systems where it tells you switch and then the other person can't. Here, it's just one Alt F to switch. I wish the other one was like that, but okay. So I'm back here. So if I make this exit, so if I enter something and this one stops, and I go back to list the things, you'd realize that it no more contains the GetPID. It doesn't exist anymore. Right? So it means that anytime someone runs GetPID, you're going to get the process ID that Linux has assigned to you. Right? Now we're going to look at how this will work when you're in a fork, just so you can understand what's going on. Right? So if we go back, I'm just going to copy my code. Okay, so I'm making a new file. All right. Now, before this, I'm going to do two versions. In one version, I'll call fork before the GetPID, and in another, I'll call fork after the GetPID. So if I do it after, so even before this code runs, do you think GetPID will print once or twice? Oh, I think I made a mistake. I just copied over. When you're copying, you have to be very careful. you can easily wipe out a whole night's work. See, I copied over it. Okay, so let me put my fork back. Fork. Right. Oh, I said I'll put it after, right? So let's start with after. So if fork happens here, and I'll compile this. Get PID 1, right? If I run this, sorry, get PID, it's telling me my PID is 3708. My PID is 3708. But meanwhile, I have two processes. Why is this so? Is someone telling a lie? Do people understand what the code is doing? Yeah. So look at the code carefully. It starts off, my PID is equal to get PID, meaning it's getting the process ID. After that, it calls what? Fork. What's going to happen? Both the parent and child, in their memory, they have the fact that my PID is the PID that they got before they split. Right? And so that means that when they print that variable, the variable called my PID, you now have that value being the same in the two programs. Right? So that's how fork happens. At the point when you call fork, you are going to get a duplicate of the process. It means that if you called get PID before you forked off, everybody will have that value in their memory. Right? And so when they are printing, now they have two people who are reporting out. They are, in this case, 3708. Alright, so before you call fork, you stored something in memory. Even without doing, okay, let me just, before fork. Right, let me do one without. Right. If I had a variable here, maybe int I, and I put 10 in here, right, you would expect that even after I call fork, both people will report 10. Right? Both people should report 10. Because it's a variable that I assigned before I cloned you. So calling getPID is very similar. All you are doing is you are storing a variable value inside. It means that after I call fork, whatever I stored before I forked off, you should have the same value. So even though I've called getPID, the PID I'm printing doesn't necessarily belong to me. It belongs to whichever process was there before the fork was called. Right. Yeah. No, we have not even had the child yet. It's still the parent. Because remember, before fork was called, that was when getPID was called. Right? I didn't call it after forking. I called it before. It means that you have the memory, because you are cloned, you have the memory of your parent. So that variable, any variable the parent has, you also have at the point of the fork. Right? The child also gets a copy. Fork will create a duplicate of the parent and give it to the child. Okay, so let's do this. Let me just do this. I will now create another PID. PID, my other PID. Right? And what I'm going to do is, after the fork, so just observe what will happen. After the fork, I am going to put a new request for getPID. So I have one request for PID before the fork, and one request for PID after the fork, right? So that you can see what will return, right? All right. So going to compile this. Oh, I didn't change the variable. Okay. By the way, some of the quiz and exam questions, I like to write a little bit of code and ask you what will be the output. Hello, okay. So now look at the new code. The first one is saying my PID is 3727. Both of them say that. But the second one says my new PID is, and one person says 3725. And that's the same as what you reported at first. And for the second one, it's reporting 3726. Right? It means that now there are two processes of the same form, but it's just a variable that was stored. The first time it puts the value in just my PID. That means that at the point when my PID was being created, when I call GetPID, it was that value that it put in. But now that they have been cloned, when they call GetPID, they'll get different PIDs because now they are what? Different processes. Right? And if I go to the second terminal and check, you will see two people with the same program name, GetPID. One of them is the parent and one is the child. That means now you have two people with the same memory. Right. So now if you can do this, then you can think of it. So the application, so that's what I've been trying to sort of hammer in for those. I know you can do Java. In Java, you code something from the beginning all the way to the end, one process. But you're trying to start to get you to think of programs that can start running, create something and split themselves into two. Right. That means that now you can properly harness your dual-core, quad-core, multi-core systems. Right. That means that Apache process can start. He can initialize himself with some values, and then what? Split off a child who will have all his memories. And the child will go do something else, and he, the parent, can what? Go and do something else. This whole multi-program, people think of multi-programming, distributed programming. This is the beginnings of it. At least on your own machine, you should start being able to think, oh, this program, what if they were running in two different spaces? And they can what? Work on some task. But in this case, they shared memory. I think on Wednesday I talked about communication. In this case, they shared some information before what? They split into two. You can keep as many forks as you want. So let me... Right. So let me do an... No, you have to keep just a loop and keep fork, as many forks as you like. All right. So, so let me add, in this case, right? So after this, there's this one. I'm going to move it. Okay. Just keep it close. And then I'm going to call fork. There'll be a lot of printing, but all right. Did I compile? Okay, compile and then run. Now there are four, right? Because the first fork created was parent and child. And then each one in his code encountered another fork. So that means that now there are four. And you can see all four who are saying, my PID is 375, 376, 377, 378. Only the first one, 375, is the actual person who started the whole process. It's the first process. That's why when I print PID, I get the old one. But when I get PID after fork and I print, I can tell who was the original and who is the new one. So this shows that's an original, that's a clone, that's a clone, that's a clone. So I hope people are seeing how this can work out. Okay, if you have an exec LP, what will happen is you are replacing your entire memory with someone else's. Right? So you will no more be going on to execute this code. So for example, let me start off here. So what I'll do is I'll take whatever I get from PID, T, so fork result. I think the book using PID really confused people. They thought it was the present process's PID, but it was the result of the fork. So what fork returns, what it will do is, when the child is coming back, in that variable, the OS will pass what? 0. And for the parent, it will give you what? The actual PID of the child. Right? So without this second fork, it's similar to what main returns, but here we'll put it in a variable for you, so that you can check and see who is the parent, who is the child. Get parents, parent. So you can get from you your parents' PID. Right. But I'm just doing, so let's do the simple one for today. I mean, once you can do this, there are others like get your parents' PID. There's that one as well. I'm just starting off with this simple one. Okay, so what I'm going to do is I'm going to print the result of this fork PID, just so you can see what they are getting. Right. So there are two things that can happen. Whenever you say get PID, the current process who is running, that's the PID you get. The only trick with this code, what this code did that was confusing, that I hope will force you to think is, it gets the PID before it calls a fork. Means that the value that it stored was an old value. I hope you understand. Which is the parent's PID. So currently, this get PID, this is actually the parent's PID. This is, right. Even though the child can print it here, that is not his PID, he's lying. Right, because a fork happened. He's saying my PID is, but that's a lie. Because that get PID was called by his parent before the parent called the fork. Right. Now, there are two branches here. One of them is when fork result is 0. I'll do one thing. Else. So these are now two separate branches. And in order to separate, I'll put for this one, I'll put C colon, so you know when the child is speaking. And P colon, so you know when the parent is speaking. So now the only difference between this and the first is now I've put a little descriptor in front so that you can tell who is saying what when after the fork. Right. So that means there will be two branches. One would be somebody who got fork result as 0 and somebody who got fork result as what? Some value. We don't know what the value is yet. But let's print out what the fork value was. Right. So I'll say fork returned. My fork result is, and then I'll print the fork result. So the child should print the fork result, and the parent should also what? Print the fork result. Just going to compile very quickly and then run this. So you can see the parent is saying that what? So P says the fork result is 3746. But look at it, the parent says his PID is 3745. His new PID, when he got PID again, he still got 3745. But look at the child. The child is saying fork result is 0. So it means the child is given a different value when fork is called. That is how they can differentiate from each other. But in addition, note that when the child finally calls to get a PID, he gets what? 3746, which is the value that was given to the parent in the fork result. So anytime a fork is called, the parent is given in its result what? The child's PID. So they are going off, but the parent now knows the child's PID by default. And that's how you can differentiate the parent from the child. Very easily. Even without saying, I want to get my parent's PID and compare it to myself. The moment you call a fork, you should be able to tell what the PID is. Another way too is, maybe before you call the fork, you get the PID, and after the fork, you call PID, and you realize that if you are really the parent, your PID before and after the fork should be the same. Get PID should be the same. One for the child. The first time, before you became a clone, it was one value, and when you change it to a clone, it's now a different value. Meaning that your PID has what? Has changed. You are no more who you thought you were. Alright, so let's look at the exec LP issue. Now, if you do an exec LP, so let me just put in an exec. Right. So right here, after this one, I'm going to do exec LP. Right. So one of the things I was saying was, if you want, so you realize that ls, you can just type ls, or you can also type ls-c1. So some of the commands have parameters. So the original command is ls, but an option for ls is you can say c1. So I'll just demonstrate that here. ls-c1. It lists everything in one column. Normal ls is this, and ls-c1 is this, right? And so what that means is, if you look at my code now, in my exec LP, here, see I'm passing a second parameter not the name, but the -C1. I'm passing it here. It means that if I want my child to behave like some program, I can also pass a parameter to that program to control what will happen with the child. Right. Now, what will happen here is you realize that the child will never print this CC. It will just get here, replace its contents, and that will be it. He can't get back the memory he had before. His code has been changed. Right. So let's compile this and see this in action. So compiled and oh, did I compile him? Okay, let me try and compile again. I was very sure I had, or I didn't exec LP properly. That's very strange. I was very sure I've exec LP'd. Okay, let me just try the default one, but still, QCC GetPID 1 output to GetPID. Oh, my ls is not exec LP. This is so strange. Okay. Yeah, that's what I've been doing all along. So what has happened to my... Sometimes it will be something very trivial. Okay. Let me try the exec LP here, even before anything happens. Right. Okay, so when I do it, it means it's running. Maybe it's not getting there. So if you look at this one, if any time exec LP happens, so I put an exec LP just here at the very top, it means that I don't even get to the fork part, right? Because the moment I call this, I'm going to replace my contents, my code with this ls. So anytime this happens, and that is why in your code, I was saying that if you are going to do something where you are going to do exec LP, you've received a command, so you're a parent, you hear a command, someone says, who am I? If you yourself do this exec LP, you will not be able to come back. It's like total recall, right? After doing that, you won't be able to come back. So you have to what? Clone yourself and let your clone go and do the work. I hope you're understanding. Because if you call exec LP, so this is an exec LP at the top. ls, your mind is gone. You can't come back. Right. And ls, for example, I can make it, maybe I'll do -C1. Meaning now you're exec LPing, but also with, GCC. Oh, I can't list it. ls cannot access. Just a sec. I think I'm leaving the null at the end. Sorry, should be. Okay, so he can list the things that are in him. Okay, so let's move this. So now we know that if we call, anytime we call exec LP, we are going to lose our memory. We are going to have the child instead do that work. So the child can come in after I do the fork, and the child will be told to go and do this ls. So compile. Right. So you can see that now. Okay. Let me slow this down. If you need to slow down output from a program, remember there was a program called less that we used to print if something's in a file. You can type, because this thing, when you type a program, any program outputs content. So if it is ls is outputting content. So if I did ls, this is ls. Oh, sorry. It lists a whole bunch. Or I can do ls-c1. It lists a whole bunch. But if I want to slow it down, I'll pipe it to less. And that means I will go and then will stop. So that I can what? One by one hit my arrow up and down to scroll through the input that's coming. We use this a lot in programming, at least on a Linux machine. If some program is spewing out so much data, you can pipe it to less. Right. So let's just slow this down so we can see what is happening in this code. Right. So you can see the child has already started printing his LS content. Right? But if I keep going down, at the end, my parent comes in and says, P, that's the fork result. That's my PID, your PID. So the child will print, but what? The parent too can come back. I hope people are seeing what's going on. So the child is doing the LS. He's no more coming back because he's been given new memory, LS. He's going to do the job of LS. But if the parents, so that means for those people who want to say, how can the parents keep taking more jobs? Right? That means all I have to do is, I can put a while loop around this. So, if I put a while loop here, while one or while true, whichever. It's 1. True will be 1. False will be 0. Right. So it means that if am I missing a closing for the while loop? Open, close. Okay, the while loop is closing. Okay. So if a while loop is around this, then it will what? It will keep repeating. The same code will keep repeating. But this will be kind of annoying because every time we do a fork, you do an LS, the parent will type something, you do a fork, you do an LS. It will just be what? Repeating over and over, which just easy to demonstrate. So I said this assignment, you can finish it in like 20 minutes. Yeah. Okay, so. Alright, so compile it and we run this. So ls goes all the way. The parent, I can type maybe how are you, and then ls goes again because what? It has forked off again. It's in a loop. I type something for the parent, I hit enter, ls goes off again. So it means that before the child gets forked, that is when I have to decide what I want to do. Do I really want to do a fork or I want to do something else? Right. So let me stop it, just so. I'll not solve the whole problem, but I'll stop it. And then come back. That means that asking the user for input. So please, scanf can't deal with spaces. So I think there is it fputs? Fget. Fput puts to screen, gets. Okay. So you use fgets. And that one can get with spaces as well. Because the assignment question, there were spaces in there. But just for simple comparison. So you have here, enter a command. So not just enter something from user, but maybe enter exit to stop. So I'm just going to make it take an exit and stop if necessary. Oh, sorry. So all I need to do is, so people are wondering, should I use, is it string and compare and so on? You just need to do it. So I'll do one, like, oh, sorry. Int my compare is equal to string compare. I'll do my command and exit. There's an n version. If you use the n version, you can specify as a parameter how many things in the string you want to compare. But this one I tend to use this one. So all I'm doing is, I'm going to compare what the person enters with the word what? Exit. And just to see if it's working, I'm going to print the result of that comparison. If the two things are the same, I'm expecting that it should be 0. So \n, result of compare is, right, my compare. Just so we can see what's happening in the comparison. But of course, it's going to be doing fork over and over and over, but that's fine. Right. Okay, enter exit to stop. I'm going to enter some junk. I think my result of compare is too far up. Right. Let me not do LSC1. Sorry. It's outputting too much information, so I'm not going to do LSC1. I'm just going to do maybe ls star.c. It will only list the C files that are in here. So I enter something, enter. Right. There should be what? Result of compare is what? 6. Because I didn't enter the word exit. If I enter something else, FJJJJ, result of compare is 1. But maybe if I do my exit, result of compare is 0. Means that when I get something from the user, I can compare and then what? If it is 0, I will know what, I know that it's exit. So using just this simple principle, you should now be able to expand your code to perform various actions. So for example, in this case, if this one is 0, so here, like this, kill, even before fork. So it means that what if I do if this is equal to what, 0, I know I have to exit, right? And then I'll do another one if it's equal to something else. If it's ls, for example, so if string compare my command is I'm doing scan, so I can't use spaces. But if the result is 0, you can do an else if. I think it's much more efficient. But so are people seeing the pattern? Yes, sir. So that means that you just do what? Get the variable and then what? Start to break it off. If this, you do it. But if I'm doing an ls, that is when I will need to do this fork thing. So let me copy all of this. Code is jumping around a bit, but let me try and clean it up and then I'll start from the top again. So it's starting off, it's going to say if my exit is 0, I'll exit. That is fine. But the second case is if I say it is list files, that is when I'm going to do a what? A fork. But I don't just fork and not do anything. When I fork, I check to see if it is the child. The child, if it's 0, that means the child is running. The child can then go off and do what? The exec LP. But if you are not the child, that means that else is implied. That means the other code will just what? Jump this if branch. So this is more or less what is happening. What you'll be doing for your code. You get the thing, you check, and then what? If you need for that action, for the specific command, to do a fork, you can do a fork. If not, so some of them you didn't need to do a fork, like GetPID. So maybe I can even add that one very easily. Like else, if string compare my command, get my PID. So this one, you just need to do a system call for it. So I'll just do PIDT. All right, so that is more or less what you have to do. You overwrite your code with someone else's code. You are not going to lose your PID. Okay, so in the loop, in my while loop, I'm not actually getting more PID. The get PID is only to find what your PID is. But anytime you do a fork, the system will create a PID for the process that will be the result of the fork. So whether or not you call get PID, you will have a PID. The list. So if that program that was calling the list, if that program also called what? Something to find its PID. So for example, let me do this. Previously, I had some code here which was supposed to be, let me see if that code is there. ./getPID 0. You remember this one, this program? This program just prints PID. What if I use that for my exec LP? That's the code that should run. So Just so people can appreciate this in its beautiful glory. I hope people are. Okay. So instead of this bin, right, I'm going to replace this with GetPID underscore 0. That means I'm in the same place. I'm just going to run. Okay, so it will be safer to just do /home/. Okay. I think I'm in the root. PWD is where I am. Okay, I'm in the root. So that means that now I'm not going to do an ls for my mind. I'm actually going to replace it with what? The other program that I compiled before. Let me just make sure that I know what to type to get this. So I'm supposed to type list my files. But when I type list my files, it's going to do a fork. And then I'm going to replace my mind with a previous program I had written, which is getPID 0. Right. So I'm going to compile this. Come on. Compile. Okay. After I compile this, I'll call getPID 1. Okay, supposed to say list files. So you can see that what? It actually ran the other program. GetPID 0. So this means that you can write multiple programs and then what? Load them in with execlp. Right. That means that possibly you have now 2 children who are going to do the same household job. That may just be a lot of, I wouldn't have written that. Because anytime you do a fork, that means that what now there are 2 people who are listening for commands from the input, which may not be what you desire. In this case, we just wanted one person who listens to the command and executes on your behalf. If the fork is outside the while, that's what you're using. So when you're writing code, you should ask yourself, what am I doing? So I'm hoping that with this, you see what your code is doing, and you can debug and fix it. Because some people are now saying, oh, I typed it and it didn't work. Maybe it's where you are doing your fork. Now, what you have here is similar to any other that you are using, your shells, like bash shell. For example, this is someone's program, BASH, bash. He wrote it, gives you a command prompt. You type something, and then you hit enter. It does something. You type something, you hit enter. Another person also called this SH. Very similar. You type something, it does something. You type something. So I'm saying that you can actually implement some of these Linux tools, where something takes a command, runs something, gets the result, and then what? Gets another command. So she had a question. You're asking for the PID of the parent, the person who started it. Yeah. Okay, so that is the first task. The second task, let me stop this so that we can have small